Hello everyone, in this video we are going to learn some problems in the topic sampling theorem and Nyquist rate. Now here these are the problems I am considering from the book Signals and Systems 2nd edition. Author name is V.OPPENHEIM. So from this book in sampling chapter we are going to discuss some problems. Now coming to the question. A real valued signal x of t is known to be uniquely determined by its samples when the sampling frequency is omega s equal to 10,000 pi. For what values of omega is x of j omega guaranteed to be 0? In this problem, they mention one continuous time domain signal x of t and it is facing the sampling operation. Now for that sampling operation, here they mention the frequency omega s equal to 10,000 pi. Here frequency is mentioned in radians. So the omega s will be equal to 10,000 pi radians. And here we asking to find out omega for what values of omega x of j omega will be equal to 0. So here we need to find out frequency omega m. So here by considering sampling frequency omega s equal to 10,000 pi, we know omega s will be equal to 2 pi fs. So after substituting in this equation, fs will be equal to 5000 h. So from Nyquist rate, we know that fs will be equal to 2 fm. So fm can be equal to 2500 Hz. So here frequency is measuring units. We are representing in Hz or we may consider cycles per second. So from this Fm, we can find out the maximum frequency omega m will be equal to 2 pi Fm. So from this equation omega m will be equal to 5000 pi. So the maximum frequency omega m we find it as 5000 pi radians. So after this frequency, the x of j omega will be definitely 0. So modulus of omega greater than 5000 pi, x of j omega will be guaranteed to be 0. So x of j omega frequencies are going to be less than 5000 pi radians. Now we will consider the second question here. A continuous time signal x of t is obtained at the output of an ideal low pass filter with cutoff frequency omega c equal to 1000 pi. If impulse train sampling is performed on x of t, which of the following sampling periods would guarantee that x of t can be recovered from its sampled version using an appropriate low-pass filter? Here they given three different cases and the sampling period for the A case is given as t equal to 0.5 into 10 power minus 3 and for the B case t equal to 2 into 10 power minus 3. For C case t equal to 10 power minus 4. By considering with these sampling periods, if we are able to reconstruct the original signal or not, we are going to find here. Here in this question, they mentioned that by considering a continuous time domain signal x of t, with this x of t signal, if we are going to do the sampling operation and output we are going to find at ideal low pass filter. And with this filter, they have cutoff frequency as omega c equal to 1000 pi. If the ideal low pass filter cutoff frequency equal to 1000 pi means the maximum frequency of this signal is also 1000 pi here. So from the Nyquist rate, we know that omega s will be equal to 2 into omega m. In radians, the frequency can be write as omega is equal to twice of the omega m. And in cycles per second or in Hz, the frequency fs will be equal to twice of fm. We can write in both the ways. Now here, after substituting omega m, here we can find out Fs as 1000 Hz. Now by considering the sampling frequency Fs of this signal, the sampling period Ts will be equal to 1 by 1000. So Ts can be write as 10 power minus 3 here. So this is going to be the sampling period of this signal. Now here they mention 3 cases. If with these sampling periods we are able to reconstruct the original signal x of t or not, we will see now. Now considering the A case, that is here I am denoting T1 as 0.5 into 10 power minus 3 here. So with this time period, F1 can be equal to 1 by T1. So this can be equal to 2000 Hz here. But here we know the sampling theorem states that the sampling frequency must be greater than or equal to twice of the maximum frequency. For this signal, the sampling frequency we find it as 1000 Hz. But in case A, the sampling frequency F1 is equal to 2000 Hz. So the F1 frequency is greater than the sampling frequency. So F1 is greater than Fs. Here F1 will be 2000, greater than Fs will be 1000. So with this sampling frequency, we are going to reconstruct the signal x of t, because if the sampling frequency Fs is more than here, like F1 is greater than Fs. And coming to the B case, here they mention t equal to 2 into 10 power minus 3. So F2 will be equal to 500 Hz. But here F2 will be less than the sampling frequency. So 500 is less than 1000 means we are not able to reconstruct the signal x of t with the sampling period. Now coming to the B case, T3 equal to 10 power minus 4. So F3 will be equal to 10,000 Hz. So here F3 is greater than Fs. So the finding F3 as 10,000 and Fs will be 1000. So with this sampling period T3, we are able to reconstruct the signal x of t. So by considering sampling period A case and considering sampling period C case, we are going to find out the original signal x of t. So this is the procedure we have to follow to reconstruct the original signal or not. Now we will see the third question. Determine Nyquist rate of the following signals. First one, x of t equal to 1 plus cos of 2000 pi t plus sine of 4000 pi t. And another one, x of t equal to sine of 4000 pi t divided by pi t. And next, signal x of t will be equal to sine of 4000 pi t divided by pi t whole square. Now, for these three signals, we need to find out Nyquist rate here. Now, considering the first question, x of t equal to, this is the signal combination of three signals. The first one is the DC signal, so the frequency will be equal to 0. Second one will be the cos signal, and the frequency omega 1 equal to 2000 pi. Third one will be the sine signal with frequency omega 2 equal to 4000 pi here. Now by considering the signal cos here and the sine signal here, the frequencies are here. Omega 2 will be greater than omega 1. So in these two frequencies, the maximum frequency component we need to consider. So the omega 2 will be equal to, by considering maximum frequency component omega m will be equal to 4000 pi. Now coming to the Nyquist rate, it states that the sampled frequency will be equal to twice of the maximum frequency component. So omega s will be equal to 8000 pi radians here. Now moving to the next problem, x of t equal to sine of 4000 pi t divided by pi t. Now this is the format. Now this signal is in the format of sinc function. So sinc of omega t will be equal to sine of omega t divided by omega t. Now x of t equal to, we can write here 4000 divided by 4000 multiplied by sine of 4000 pi t divided by pi t. Now from this we can write this as x of t equal to 4000 multiplied by sinc of 4000 pi t. Now in this function the maximum frequency component is omega m will be equal to 4000 pi here. So from Nyquist rate, omega s equal to twice of maximum frequency omega m, and omega s will be equal to 8000 pi radians here. Now we will see the signal x of t is equal to sine of 4000 pi t divided by pi t whole square. To simplify this one, here we will to consider a principle. Sine square t is equal to 1 minus cos 2t divided by 2. By using this principle, if we are applying on the signal, we can write x of t as 1 by pi t whole square into 1 by 2 minus cos of 8000 pi t divided by 2. Now here this x of t has one signal here. So in this signal, there is no frequency component. And coming to this one, here is a cos signal. And here the frequency component is 8000 pi. Now this is going to be the maximum frequency, omega m equal to 8000 pi. So the Nyquist rate, omega s will be equal to twice of the omega m. So after substituting, we can find omega s as 16,000 pi radians. So this is the procedure we need to follow to find out the Nyquist rate. Thank you for watching this video.